Supervised machine learning relies on labels, clear target variables that act as a ground truth answer key. Unsupervised learning lacks this roadmap. We ask an algorithm to find order from the chaos of unlabeled data, identifying patterns where no predefined answers exist. Think of it like organizing a massive box of toys without instructions. The algorithm must group the items purely on the physical and mathematical similarities it observes between individual features. This scatter plot shows a raw customer dataset where we are tracking age against income. Looking at this distribution, we want to segment these customers into distinct groups to better understand their behavior. To find these segments, practitioners typically start with k-means clustering. It is the industry standard for identifying groupings in unlabeled data. The process begins by defining k, the number of clusters we want to create. The algorithm drops k random starting points, or centroids, into the data space to begin its search. But because unsupervised learning has no explicit labels to check its own work, applying a default algorithm without understanding its geometric assumptions can lead to conclusions that are mathematically sound but logically flawed. K-means calculates distances from every data point to each centroid, assigning records to the closest star. It finds the center of gravity for each group, moving the centroid to that new center. This assign and update loop repeats until the cluster boundaries are finalized. For this to work, we need an objective way to choose k. We do this by measuring the variance within the clusters, a metric known as the sum of squared errors, or SSE. This graph plots the SSE across multiple values of k. As the clusters better fit the data, the error rate drops. The point where that drop-off abruptly slows down, forming this elbow shape at k equals 3, suggests the most efficient number of clusters. However, consider how the algorithm sees raw numbers. If income ranges into the thousands while age stays in the tens, a shift of 10 years is seen as 10 times less significant than a shift of $100. The math is dominated by the larger scale, effectively ignoring the age variable until we scale both features to the same range. Even with perfectly scaled data, k-means operates under a strict invisible constraint. Because it is anchored to a central point of gravity, it assumes all clusters in the data are perfectly spherical. In reality, data often form shapes that are far from globular. To test this, we can use the noisy circles dataset, which represents nested continuous phenomena often found in complex systems. This panel shows k-means attempting to cluster nested rings. Because it looks for a center, the algorithm fails, slicing the rings in half rather than recognizing they are separate, overlapping structures. This failure happens because k-means is blind to curvature. It cannot perceive a boundary that loops around a center, as its math only understands proximity to a single central point. To solve for these geometries, we must shift away from centroids and toward hierarchical agglomerative clustering. This is a bottom-up approach. It begins by assuming every single data point is its own unique cluster. The algorithm searches for the two closest points and merges them. It repeats this process step by step, binding neighbors into larger groups. By defining distance based on these nearest neighbor linkages, rather than a center, the algorithm can follow the winding, continuous path of a curve. As we see in the bottom left panel, this allows the model to correctly isolate the inner ring from the outer ring. By prioritizing proximity to a neighbor over proximity to a center, we fundamentally change the types of patterns the machine is capable of perceiving. The drawback of the agglomerative approach is that it doesn't use a k-value to tell it when to stop. Without a limit, it will eventually merge everything into one giant, useless group. This dendrogram maps our merge history. The x-axis displays data points. The y-axis records the exact distance they merged. We find our segments by drawing a horizontal line through the tallest vertical gap uninterrupted by horizontal branches. Crossing 3 branches indicates 3 natural clusters. The dendrogram translates the merge history into a structured map of dissimilarity. It reveals exactly how the clusters emerge at different levels, allowing for a systematic selection of the final segments. Hierarchical clustering handles complex shapes, but shares a structural limitation with k-means that often goes unaddressed. Both algorithms are designed to force every single data point into a cluster. They cannot ignore a record, regardless of how distant or illogical its placement might be. In a data set of financial estimates, most reports will gather around a consensus. However, there will inevitably be extreme, irrational outliers that reflect errors rather than valid predictions. When an algorithm is forced to include these outliers in a legitimate segment, the mathematical center and variance of that group are corrupted, degrading the model's accuracy. To build a reliable system, we need a method capable of mapping weird shapes, and it must have a built-in mechanism to ignore noise. Achieving this requires a transition away from distance and towards spatial density. This is the philosophy behind DBSCAN, density-based spatial clustering of applications with noise. It targets tightly packed regions while filtering out everything else. DBSCAN uses epsilon, a strict radius around a point defining its neighborhood. Min samples is the minimum points required inside to be dense. Meeting this threshold creates a core point. Points inside this radius lacking their own neighbors are border points at the edge. Any point that fails both criteria, lacking neighbors and having no core point nearby, is labeled as -1. This is a noise point, which the algorithm explicitly ignores. DBSCAN chains adjacent core points together to form clusters of any shape, automatically stopping the growth the moment the data density drops below the threshold. While other models would tether an outlier to the nearest group, DBSCAN leaves it unassigned, isolating anomalies and protecting the integrity of the segments. The reliability of your model depends on matching the algorithm to your data's topology. Use k-means for simple spheres, agglomerative for nested curves, and DBSCAN for arbitrary shapes surrounded by noise.